Welcome to another CO2 Experts. So happy that you're all here, taking the time to come in and hang out with us. There's lots of stuff that we're going to be sharing and learning. Got my good friend Chris here. We've been doing CO2 design courses for over a year now. We got fundamental CO2 design. We got advanced CO2 design, 6 weeks, 12 weeks. And me and Chris are always keeping in contact, learning from each other, growing from each other on CO2. And he was on CO2 Experts late last year, and we dove into troubleshooting CO2 system that having piping issues. So if you haven't listened to that on the podcast yet, go check that one out or go check it out on the YouTube channel, because Chris dives into all the top things that we could run into in piping issues in CO2 system. Now, today, we're going to be diving into really some controls and common issues, troubleshooting and support. And Chris brang and invited one of his good friends who is really another CO2 expert who really cares about the industry, supported thousands and thousands of technicians out there, and really cares about helping others. And this is what I love about our industry and the people that come here and come and share their knowledge with us, is that we really want to help the industry grow, uplift the industry. Chris, John, welcome to CO2 Experts. How are you guys doing?
I'm doing great, Trevor.
Thank you for having us.
John, why don't you do a quick introduction of yourself and a little bit about your background?
Yeah, so my name's John Rothery. I've been working in refrigeration now for the last 26 years. Started as an installation engineer, then moved into commissioning. Following that, moved into account management. So I manage an account in the UK on one of the leading supermarkets over here with 265-ish sites I was covering. After that, moved over to DNA, worked alongside Chris just to learn more of the technical insight, really. So yeah, it's been a good journey.
Oh, I love it. So, because you started out in the field, just like Chris started out in the field, and that's where we get our hands-on experience. We're learning out in the field and what works, what doesn't work, and then you moved along. You know, you continued your journey along, just like all of us. We all started. Chris started in the field. I started in the field. And then we moved our journey along. And I talk about this with technicians all the time. Is like, this is where, when you're in the field, get as much experience. Throw yourself at things that make you uncomfortable. Because when you learn that on call, or when you have those big problems and you figure that out, that is going to just set you up along your journey, because now you've been supporting technicians working for a large manufacturer, just really helping the industry grow, because you've been doing this 26 years. Good on you, brother. You're still in it, plugging away. And I'm hoping you're still loving it, because I still love it. I still love it.
Yeah, every day is a new school day. Again, it's sort of like you say, just keep going. You will face a problem you can't fix. It happens to all of us. Make friends, share your knowledge, and build that foundation. And then obviously you can reach out when you need it. Yeah.
And I love that. And that's the thing. We are here to help support you to get to your next level. Our industry is not a massive industry. So we're here to help each other grow. That's what Refrigeration Mentor is all about. Omega Solutions. Chris, super excited about our conversation today, brother, because we're going to be diving into more technical aspect of CO2 and things that we really want to understand, some common issues to really help people who are listening on the podcast, watching on the YouTube channel. And once again, rewatch this. And if you're seeing this, posts on social media, like this, post this, comment on any of these social video clips that we put out there, because we want to share this knowledge with more people. We get in front of more people and they want to start learning about CO2 or start learning about refrigeration. That's what we care about. We want to help others. So Chris, how you doing, brother?
Very well indeed, Trevor. Very well indeed. Thank you for having me back on here. Quite enjoyed doing these CO2 Experts. I think this is the fifth one I think we've done now? It was CO2 Mondays a couple of years ago. We ran through some design on cold room construction, heat load calculations, condensers. Last year, piping problems. It's actually something both John and I had encountered several times in the past on existing installations. Worked through together to come up with solutions, identify whether it was undersized or whether it's an issue of the actual, or even the expansion valve. And to be fair, some of these issues we'll run through today on Superheat can also manifest as issues in pipe sizing as well. So a good way of just being able to confirm what are we looking at and how to overcome it.
Yeah, and we got a design course, advanced design course coming up very shortly. So if you're interested in that, any of you, reach out to me, shoot me an email, DM me, and we'll try to get you into that course because we've got a couple spots left. So super excited that. Chris, why don't you take it away, brother?
So hopefully most people are familiar with what superheat is in a system for refrigeration, but let's just clarify it for everyone in case they need a refresher. When we talk about superheat, we're talking about the temperature of a refrigerant when it's raised above its saturation temperature at a specific pressure. This will vary per refrigerant type and also for each application. Controlling it ensures we have sufficient heat absorption within the evaporator to actually absorb that heat that we need to produce our cooling effect, whilst preventing liquid refrigerant or anything which hasn't boiled off yet from reaching the compressor. So it protects our system at the trade-off of slightly less efficiency by not having a completely flooded evaporator. This boiling off in the evaporator is what we call useful superheat. So when we talked about pipe sizing before, we raised up the term of useful superheat versus non-useful superheat. Useful superheat is anything inside the evaporator which boils off that refrigerant past its saturation temperature. Non-useful superheat would be anything which then gets absorbed between the outlet of the evaporator and the compressor. Too much of that will cause the compressor to be effectively have insufficient cooling going to it, which will result in high discharge temperatures and affect the properties of the oil and refrigerant in the system. That's a bit beyond the scope of this, so let's just look at useful superheat and how we control that. That's calculated as the difference between that refrigerant's actual measured temperature, which we could detect with a probe or a sensor bolted onto the pipe, and then that saturated temperature at the same pressure. So back in our on a TXV, it will sense that superheat basically just by the refrigerant in the little vial sensor increasing and decreasing in volume as the temperature on that pipework changes. With electronic expansion valves, we only have a probe, we have a transducer, maybe to measure the pressure, and then we need to have a controller which then converts those signals into an actual process to drive open or close our expansion valve. On the right-hand side, we've got a very, very basic image of what an evaporator coil will be. Refrigerant will flow in, and as it gets towards the outlet, it will start to boil off. Just shown as a change in color on here, just to give a bit of a visual indicator. And as we lead into how we control it, we can have issues of low superheat or high superheat. So typically, rule of thumb, we want probably between 4 and 10K superheat on an electronic expansion valve. Different evaporators and different manufacturers out there will call for different values to be used in their systems to obviously control it and maximize what they class as the usable heat transfer through their coils versus risking possibly liquid flooding back to your compressors. So when we talk about low superheat, no refrigerant has boiled off, so there's obviously no chance for it to heat beyond that saturated temperature. Another term we use for this is a flooded evaporator. It's completely full of liquid, it's flooded. We get really good heat transfer through this coil because liquid molecules of refrigerant absorb heat a lot more efficiently than vapor molecules. We get no vapor formation, but we do now risk liquid flooding back. Whereas on the other side, we have high superheat, where that refrigerant is boiling off almost immediately as it goes into the coil. You may be only using 50% of its usable actual surface area. So we get very low heat transfer. Where this refrigerant gets warmer and warmer because it's already boiled off, we have very little or no suction cooling back to our compressors. That then results in high discharge temperatures and high discharge superheat, which can lead to refrigerants breaking down and oil damage as well. Oil damage probably much more common on CO2 systems with these high discharge temperatures rather than the refrigerant breaking down properly because obviously it's a single chemical compound.
So Chris, I have a question. I do lots of like supermarket trainings. If you just want to go back to the slide, and like I train a lot of CO2. We got a lot of CO2 courses. I had a few times in the supermarket trainings where a technician would say, "Hey, Trevor," I had times where if the TX valve was flooding the evaporator, so I'm getting a lot of liquid, so it's flooded. So they were flooding back, but they weren't getting the heat transfer out of the coil. So they're like, well, it's not boiling off. So it's not making that not getting that latent change. Could that affect, if low superheat, could that potentially increase the temperature of a case if you ever had flooding, or would it drop the case? I'd like to drop the temperature. Can you elaborate on that too, when it is flooding, or that coil that is supposed to boil off, but it's all liquid in there?
I've not encountered the lack of duty from it, because you are picking up so much heat. I suppose the only alternative would be if it's flooding through at such a high velocity that it doesn't have time to actually pick up the heat. It's unlikely to happen in a system like this, in my opinion. I'd be interested to see. It might be the different configurations on those. Are they actually designed to operate as flooded cabinets? Who knows? Yeah, I've not got a story to tell about that one. I don't know if you've encountered that in the past, John.
So yeah, I mean, if your coil's flooded, say your EEV stuck open, then obviously your coil temperature is going to drop, and you'll end up with sort of ice formation, lack of airflow, lack of heat transfer, and it sort of just eventually compounds the issue to the point where you start seeing flood back to your compressors, oil washout, all that kind of stuff. So yeah, I would say, yeah.
Yeah, so there's a huge compound effect in both of them, low superheat or high superheat. And this is just in refrigeration in general.
Yeah.
Awesome. Thanks, Chris.
Good stuff. So when we look at actually controlling superheat, as mentioned, TXVs just control that superheat using a sensing bulb, which that increases pressure or decreases pressure on a spring inside the valve body, which will open or close to allow more or less refrigerant through. With larger systems and for more close control, we use electronic expansion valves. Most supermarket applications out there will likely use these nowadays. They may be AKV, so pulse width modulated valves, which just open and shut over a certain period of time, or a certain number of times within a timed period. So say 6 seconds, if you wanted it 50% open, it opens for 3 seconds, shuts for 3 seconds. Or you get what we call stepper valves, which will wind themselves in and wind themselves out to more closely match the amount of refrigerant which it needs to let through. So if it was 50%, basically it should wind up to be 50% of the openable area to allow 50% of refrigerant through. It doesn't quite work like that in terms of how fluid flows through a valve, but for the purpose of today, that's as accurate as we need to be. So on a supermarket, each evaporator needs to actually know what the pressure is equivalent to be able to calculate this, to calculate the superheat. Depending on how much pipework there is, you may be able to use a single transducer to know the pressure all the way back at the compressor rack. If it's a small system, it will ping a signal across and measure that pressure every 10 seconds. That may be enough because you've only got 30 feet of pipework. With our velocities, that refrigerant gas is getting back to that very quickly. There's no delays in measuring the pressure versus that refrigerant property. On a larger store, say you have a 40 or 80,000 square foot store with 200 cabinets, if you only had one pressure transducer at your compressor rack 500 feet away, by the time that signal reaches that and sends a signal back to the controller, that information could be probably a minute out of date. You could have started pumping your system down by then. It'll have no idea what pressure it's supposed to be and will give you completely inaccurate superheat values. So at that point, you can almost group similar cabinets with a single pressure transducer. So on the schematic we have here, we have a transducer on 3 cabinets, another one shared between 7, and then one for a cold room. They could all be spread out 200 feet apart, but it gives that closer control about that localized pipework. You could even go further than that and have one on every single cabinet, which I know some end users do. You get excellent control, but at much higher costs as well. So it's a trade-off between complexity, control, and cost.
And so what are your thoughts on that? Like, for me, I've always every coil have a transducer, because now I know what that specific valve is doing, like the EEV, as well as that coil. Now with a transducer getting, for an example, those 7 cases, as long as it's piped properly and you don't run into any issues, those valves will work great, but what happens if you have one transducer but you have 2 frozen up coils? How does that affect all the other cases now with one transducer?
They're best shared across it, I would say. So if we took that island of 7 cabinets, for example, 2 of them were iced up, 5 of them are operating okay. First point I would look at is it's probably not transducer related. It'd be more of a controller issue in terms of, say it is a Superheat issue of miscalculating the valve opening positions based on those transducers. Because if 5 are working okay and yet 2 aren't, well, you can almost rule out the hardware issue there, because otherwise all 7 would be faulty. Trying to think what else you'd have them.
Sort of seeing local low superheats on those fixtures that are iced up, so fans tripped or something like that. The risk you've got with a common transducer on an island is if that transducer fails, a lot of the controllers have a backup value you can input. So say that's set. So all those cases would then go, well, we've all got the same superheat, we'll all start controlling the same way. You run the risk of getting flood back a lot quicker, because all those valves will then start driving to an inaccurate reading. Whereas if you've got one transducer per fixture, you can see it quite clearly that, if you've got all that extra redundancy in the system, that if a transducer does fail, it'll be that one cabinet. And if the valve goes into a sort of emergency operation of 0 to 100% modulation, you're not going to get so much flood back to your compressors.
Yeah. And I think that is the big thing right there. So thanks for pointing that out, John. It's that inside all these controllers, there are going to be different parameters. And honestly, most technicians probably don't know that there's a probe error parameter that'll say, okay, it goes to 50% valve and the valve stays at 50%. So that 50% could either flood back to the rack, or it could overheat. Either or, you don't know, because you're just putting it at a manual. It's like putting overriding into a manual position where it's not going to modulate the valve. Is that correct, John?
Yeah. So you've got the manual sort of fallback, and also you've got the transducer fallback, haven't you? So if the transducer fails, you set it to say 20 bar. The transducer's off, but you still see that reading on your controller, so it sort of hides the issue. If you've got multiple transducers, you can compare one case to another, and it's pretty apparent, that it's not moving and it's just flatlined on your graphs.
Yeah. And that's it. It's easier for troubleshooting. It is more upfront cost for the end user. But it's with CO2, which I am loving, there are so many more trends that we can get in the controls. So you can look at an actual system. You get the superheat, you get the suction temperature, suction pressure, you get the discharge air, the supply air, the defrost termination. And this stuff we did, it's not new to the industry. We had this 15, 20 years ago. It's just that it's more apparent now because more people want control, they want visibility. And for me as a technician, it helps me troubleshoot so much faster cases. What are your thoughts on that? Because you do a lot of support, John, on helping technicians out in the field. What are your thoughts on working with the newer, more electronic based system versus the older mechanical ones? Because you've done both, right? And what are your thoughts on the differences?
Yeah, so obviously the new sort of systems, I can dial into a store remotely. On the contract that I was working on, I could actually look at the fault, diagnose the fault potentially before the engineer even arrived. So it's good. It's great for a steer. If I'm seeing flood back low superheat on something, I can shut it down remotely as well, protecting the compressors, because obviously you got the big cost if you start getting flood back through a cabinet. For the sake of a transducer, and you're risking compressors failing, etc. It's a no-brainer, really. But yeah, it's great. It is great.
Yeah, and this is what I talk about to a lot of technicians in our programs, and because there's some people that are still hesitant. Oh, I don't like the controls. It's just so much because it's overwhelming and it's new. You've been doing this for 15, 20 years working on electronics. We're in supermarket. We've been doing it a long time, but there's still a lot of people out there that are hesitant of all these electronics and saying it's making it more complicated. Do you feel like it's making it more complicated, or it's just overwhelming at first and there's a bit of a learning curve, John?
It's a learning curve. So say, for instance, a manufacturer, Corel, they've been around for a while now. It's just knowing and interpreting the parameters that you need. It's definitely overwhelming without a doubt. One of the issues on, say, the Corel front end is when you get a graph and you switch between various readings, you have to check the scales, because you can set it to auto scale, which makes things maybe not align. You can have your air off looking, lower than your air on, but it's because it's adjusted the scale within that set range, because that's what it sees on the probe. So yeah, you've got to be, I don't know, more sort of focused on what you're looking at.
Yeah, no, I appreciate it. Chris, this is such a great conversation. Let's just keep diving into this Superheat control.
Sorry, something just to jump on that, we'll look through it in a minute, but one of the issues we've actually encountered in the past is with those controls, sometimes it's buried deep in manufacturer's literature, but say you have a 60 bar transducer versus a 90 bar transducer, you need to go into the controllers and set up which type it is. Otherwise it will not read correctly and you will get these funny values, and it
discrepancies.
The system just will not work as it should, which can lead to some not catastrophic failures, but definitely some big issues that technicians could do without. So yeah, make sure it's commissioned as per all manufacturers' set points and recommendations, and obviously a key one to drive home.
And I think I like that, Chris, because I think a lot of the things is that it's new to a lot of people. And it's understanding each one of those parameters and what they're doing. And I've read so many control documents and case controllers. It can be confusing because one controller manufacturer says it one way, another one says it a different way, but it does the exact same thing. So it can be confusing. Have you guys noticed that in some control documentations from the manufacturers?
Yeah. Without doubt. I mean, another thing to sort of be mindful of is when you've been doing it a long time, you sort of get the mindset that you'll be driving to site to fix an issue, and you'll think, oh, I know exactly what that is. You'll go there, you'll do it, and then you'll come away, and then it's something else. It's taking a step back, having a pause, and don't assume the fault's going to be the same as you've experienced elsewhere. It's literally just take a step back, take your time.
Yeah. No, I like that because I've done that so many times. I'm driving to a site on call and I'm like, I got the problem. I know it. You know what I mean? Yeah. I know what it is. I've been there earlier in that week or the week before. I know what it is, and get there. And then I'm thinking of that problem the whole time. And I spend 25 minutes and it's not even that. I just wasted 25 minutes instead of taking a bigger look at what's going on in the whole picture, understanding, talking to the right people, and then actually looking at that problem, not the problem that I was thinking driving to the site. So I appreciate that, John.
Right. So let's jump into the symptoms that you can get with superheat. So across the board, both high and low superheat, but we'll look at both. So big one which happens quite often is debris inside the expansion valve. So whether they've been brazing without purging with nitrogen, or something's fallen into a pipe during installation, and it's finally found its way to the expansion valve, and it's just enough to stop the valve from shutting fully. And at that point, you try and drive a valve down, closed, the signal thinks it's shut, but yet refrigerant's still going through. That's going to be forcing it to allow excess refrigerant into the coil when it doesn't need it. If there's not enough heat load to boil it off, that liquid is then going to reach back to our compressors. Slightly along the same lines, an oversized valve, where you've got very little control at low load conditions, the tiniest bit which will open will allow a lot more refrigerant through than it needs to. Again, not enough load to boil it off, liquid's going to reach back to our compressors. What I find as well is if there's oil logged in the evaporator, there's a lot less heat transfer. It's insufficient heat transfer to boil off because it acts as an insulator. That refrigerant will still go through and again reach back to our compressors. And then lastly, as we've already talked on, poorly commissioned. So if those valve parameters aren't set up correctly, if it's not reading the right transducer range, you'll get overfeeding of liquid. And again, it will reach back to our compressors. So where we have here, low superheat, I always consider is a lot harder to pinpoint the real cause issue than high superheat faults.
Yeah. One of the things that like in some of the intro to CO2 course, I have a lot of technicians who come in and they're just starting to learn about CO2. They've worked on HFC units before, but they didn't have so much as the controller and the superheat, like being able to see it as much. And now I'm teaching them how to get into the trend graphs. So looking at the trend graphs, and one of my favorite ones is opening percentage of the valve. Watching the opening percentage. And so you go to the trend graph and they'll bring it up and I'll say, okay, let's go back 3 months or 4 months and let's look at the trend graph of that valve opening and what the superheat was. And then all of a sudden you can start to see the temperature starts to rise up and then the valve is starting to rise up more open. So instead of it running around say 40 or 50%, the valve is running at 80 or 90% open now to try to maintain the same temperature. So when you're I find it so much easier to troubleshoot a case when you have all these checkpoints. Before, when I was in the field and on the tools, I had a set of gauges and I put it on one case and my temperature probe, and I had Cooper and say yellow jacket, and then nothing was logging. So I just seen it at that moment in time. And I walk away, go to check another case, and then I come back and it's different. I'm like, okay, well, what's happening? Now with the trend graphs and these controllers, and really any manufacturer now with case controllers, they're doing a great job with the logging features. As long as it's set up and you have the temperature probes, it helps me so much. And then showing these technicians in these CO2 programs, they're like, I never thought of that, because I'm not used to seeing how a TX valve reacts and what percentage the TX valve is open. We only have a few set points mechanically to check. What are some of your thoughts on that, Chris? We'll start with you, Chris, and then we'll go with you, John.
So honestly, having that visibility over a prolonged period of time is invaluable. And for troubleshooting, literally yesterday alone, I was actually chatting to my one of my former apprentices who's now an installation engineer, and he was just commissioning a small freezer room, and he was wondering how long is it going to take before I head off because he's got a 2-hour drive home. So I was like, I'll dial into the site, have a look, and you can see it's dropping by 5 degrees Celsius every 5 minutes, basically. It's like, I was like, well, you're plus 2 degrees now. You got to get down to minus 21. You'll be home in, ideally sort of 25 minutes, or you'll get to leave. I think it took about 30 minutes in the end because someone had opened the door. And he's like, oh, that was great. And then I could pack half my tools away and have to shoot off. So it's just having stuff like that. It helps you program your day as well, as much as anything. And can maximize your workforce. And if you have someone sat in the chain, dial in, it's like, that's coming down quite nicely. You probably don't have to wait half an hour before you start really doing your paperwork, start packing your tools away before you start leaving site. Something like that. It's invaluable. I'd love to have had that when I was on the tools.
Yeah, me too. What about you, John? What are your thoughts?
Yeah, no, it's a great feature. And like you say, you can sort of spot a step change when, the valve's starting to become blocked. And like you say, it starts increasing the percentage opening, or say your suction probe falls off. It's still getting the temperature from the case, or it's, becomes slightly detached. Then you'll start to see the valve sort of go 0, 100%, 0, 100%, where it's not seeing the superheat it wants to calculate. So yeah, it's good for diagnosis and sort of pinning things down without a doubt.
Yeah, no, and I totally love looking at the trend graph. So if you're getting into CO2 and you're starting to see more case controller, I highly recommend starting to learn how to read the trend graphs, because it does take a little bit. Which one should I use and which one should I be watching and monitoring? But for sure, when you're watching the defrost, when it goes into defrost, out of the defrost, into defrost, out of defrost, and we'll see these consistent things happen as long as it's fine tuned. Because that's another thing that I train a lot in my CO2 programs is how to properly fine tune it. Because when you set it up day 1, day 3 or day 4 or day 5, as people start putting more product in, you get customers in, doors opening and closing. That could change the humidity in the store. That can change the dynamics of that specific case and that specific location. So I think it's super cool. So And the very first point there, Chris, debris inside expansion valve. I think that is one of the biggest ones. When I used to work for the manufacturer and doing a lot of electronic valve training, and I would go to events and I would talk to all the competitors, we had the same thing as a manufacturer. Like most of the issues were debris inside the valves. So this is something that really you want to take a look at, because all the big valve manufacturers are doing a good job. They got quality control. They're spending millions of dollars to make sure a good product comes out. Do issues happens along the way? Totally do. But there should be absolute zero dirt, debris inside, really, in a refrigeration system. There should be nothing. But we know we're supermarket refrigerator. I put a lot of dirt in the systems over the years. So just be aware of that stuff. Make sure the debris is out of there.
The one thing, when I was an apprentice, trying to decide if something was an issue with high superheat versus low system charge always threw me. And it was only after really I probably came off the tools that I really started thinking and getting more to grips with it. So just other symptoms, etc. But main way to tell, I find, is the suction pressure okay? Is the discharge pressure okay? If there's enough refrigerant in the system still, your discharge pressure isn't going to be low. That refrigerant's got to be withheld in the system somewhere. Your liquid, if you can check the liquid side or intermediate side, you should have sufficient pressure there, because refrigerant is backing up within it. It's not going through the valve, and that's what's causing the high superheat on the other side. Whereas a system low on refrigerant will be sending out refrigerant through, it'll be boiling off very quickly because it's not allowing an awful lot through. But there's also not a lot behind it either. So it's having that. Also, if you've got a sight glass to check, high superheat, you'll have no flashing in the sight glass, or ideally not. System low on refrigerant, you'll see the bubbles in there. There's just not enough refrigerant filling up that space. Your liquid is already boiled off well before it even reaches the sight glass. So that's one way of checking. Also, low refrigerant charge will occur across the system, whereas incorrect valve commissioning, etc., or it's not opening enough, should appear just on one or two fixtures. If it's across the entire system and your site's been commissioned incorrectly, well, that is an item there, but hopefully be able to identify that based on, you probably have to dig a bit deeper into it to check.
I was doing supermarket training last night with some students, and we were getting into low ambient control. And so here in Canada, like right now here, it's like -5 Celsius or 20 some Fahrenheit. And this is where they're like, well, how do I tell the difference between like a low charge or the refrigerant stuck somewhere else in the system? John, do you have any experience with that?
Refrigerant logging? Yeah, I have done, to be fair. A lot of it should obviously be designed to sort of push it out of the gas cooler and what have you. Keeping the gas coolers clean, obviously checking if you've got false load on the gas cooler for sort of heat boost, that sort of thing. Checking they're not iced up. It does happen, and you can get the login. Generally, if checking charge, etc. If you lose gas, you lose oil as well. So it's always worth comparing the two. An issue I have seen with regards to charge, if you're checking your vessel, is the RPRV, your flash gas valve. If you've had power cuts overnight, if it's a brief power cut, the valve starts driving close, it comes back on, so the valve can actually go out of calibration. So it's always worth checking your valves are calibrated as well if you're getting sort of oddities with fluctuating levels in your vessel.
That's a good point. So the flash gas bypass valve or the receiver valve, it's functioning, and all of a sudden power's killed.
Yeah, that
potentially there could get the valve out of line of where the controller's controlling it.
Exactly. So yeah, it doesn't know possibly where it is, because if the power's not off long enough for that controller to drive that valve fully to zero, it can go out of calibration. So it's always worth, just checking they're calibrated.
I love that. Always learning something. Great.
So what we've got next is a very, very simplified sort of on-site check process you can go through. So we've got an example scenario here of an intermittent low superheat alarm. and finding occasionally as liquid flood back to compressors. Say one of the 4 compressors on site has been flooded, it's got valve damage, whatever, it's been sent away to manufacturer, new one fitted, and you're starting to get the same issues again. So number one thing we found, which also relates back to what you just said about the controls and being able to look back historically, has the problem just started? Well, if not, let's go through our normal checks. Check airflow, for example. Make sure it's not, the refrigerant's actually able to pick up heat into that coil. Check control settings. Check that fans are active. Check transducer output values. So as the transducer converts a pressure signal to a voltage, check that actually relates to what the pressure actually is inside the system. So you may have to put a gauge on to actually physically measure that pressure rather than just relying on what that transducer is telling you. And then also check whether the expansion valve drives open and drives shut. If that problem has just started, next thing we check is, have the controls been changed? Try and narrow it down to whether it's a software or a hardware issue. If the controls have been changed, it could well be something to do with that. So check those settings and amend if necessary. Monitor it. If the fault reoccurs, it's unlikely to be controls related. If the controls haven't been changed, it's been like this since day one. Not like this since day one, but nothing's happened to the controls. It's probably hardware then. So again, check airflow or water flow if it's a pump system. Check transducer output values and check that EEV drives open and shut.
I've seen it where too. I had a student in my CO2 intro course maybe a month ago. Last class, he was saying that he was at a site and the vessel, the flash tank, was reading, the transducer was reading 800 psi, so upwards to, not say 50 bar, I guess. And really in the tank, the pressure relief wasn't going off. He was like, what is going on? So the system shut down, but the pressure relief was like, it was that much pressure in there. And so what he did, he took his high pressure gauge, put it on the flash tank, and it said 580. He's like PSI, so around 40-ish bar. And he's like, what's going on? So he actually pulled off the transducer and was full of oil. He just emptied it out of oil, put it back on, and it read correctly. So some things can be a little tricky like that. And I've talked to a few manufacturers do a lot of support, and they've seen a lot of technicians like cut valves out or replace valves for actually a transducer issue or a wiring issue to a transducer. John, do you have any experience with that?
Yeah, I've seen that before, especially oil logging. When they've been installed and it sort of forms a trap and the oil migrates and sort of hits the transducer, causing it to read incorrectly. I've seen that before. Obviously, one check you can do if you've got a backup controller is compare the two, just to sort of as a comparison. I think we got that on the slide as well somewhere. So yeah, it does happen. I have seen it.
Yeah. One of the issues I've found in the past is that work's been done on an island, and the transducer's been left valved shut. And afterwards, then all those controllers are linked to this, but that pressure is not changing because it's trapped in that short section of pipework, and results in incorrect and liquid flowing straight back to the compressors. And thankfully, not quite a large enough island to really damage the system, but needed investigation. And that's the issue. So again, it goes back to commissioning checks. Make sure that transducer is actually reading what it should be. You'd think it'd occur to you when it's a consistent 28 bar all times for a week. That system's working really well. Consistent suction pressure. No, it's because it's not reading correctly. So that's one of the things we can check on our, if it's a transducer. Sort of Ray touched on is there, for example, a difference in pressure between a primary and backup controller? What we can do there is check that again with a physical gauge, put it on the system. And also you can swap between different transducers to rule out a wiring issue as well. If you've got similarly located transducers, check between, does that controller now show a different signal? If so, yes, it's probably not a wiring issue. If it doesn't show a difference, well, there's something, if it's unlikely both those transducers are going to be faulty, it's probably the wiring. And then again, if you have a constant pressure reading where you've got a different value shown by the transducer versus that physical system. So again, we put our gauge on the system, check the values which are inputting to the controller. So check the voltage, check that transducer range is set up correctly in the controller, make sure it's whether it's a 60 bar, a 90 bar transducer, or lower if it's a lower pressure system. I don't tend to come across anything lower than a 60 bar transducer on CO2 nowadays over in the UK. I'm aware it was in the past. And yeah, basically just do your checks and do your due diligence.
I think that is important too, is to understand the system. Like understand the system you're working on, because there's so many. I train so many people from around the world in different countries, and then come in and we're learning CO2, and then like you just said, like most of the system you see now are 60 bar, right? 800 and some PSI, standstill pressure, where there's tons. All the ones here in Canada, I don't know many that are that high. Like there are some, but most of them are 40 bar systems, standstill pressure. So depending on where you're at in the world, you really want to understand that specific system that you're working on. And that is key to your success, because I really try to teach technicians that they can go work in the UK, or they can go work in Germany, or they can go work in Australia. But it's understanding that system. And then, like you said earlier, Chris, I really like that point. Well, is that the right transducer? Is that a 0 to 60 bar transducer, or is that a 0 to 30 bar transducer, and it's not getting the proper range? And so now that valve is working way erratic, still maybe working a little bit, but it's not reading correctly. So the range is off.
Right. So next few slides we've got some other photos which John's kindly shared with us of things he's found in his time. So as we spoke about the debris within the valve earlier, just on the right-hand side, you can see just how much debris is built up on that filter there. So again, goes to a cabinet, high superheat, product alarming, cabinet not achieving temperature within a correct time span. Presumably that was off of defrost. Whereas all the other cabinets on that shared header, that pipework, were achieving temperature within the right set time limit. It's a fault specific to the cabinet. So again, I presume, John, you go through, check everything over, strip the valve apart, and find that. That's a pretty obvious cause there.
That's it. You'd see that step change on your trend with the valve, gradually opening more, as Trevor pointed out earlier. It's a good feature to have, without a doubt.
Yeah, I think so too, because there are some valves out there that don't have filters before it. And I think most of the manufacturers today do at this point. You may not know that, like it may not be like what you're used to in a TX valve, where it's very noticeable. Like this one here is not noticeable. This is inside. You actually have to take the valve apart to look at, pump down the circuit safely, pump all the refrigerant out, and then reclaim whatever's left in the lines to push it in. And this is what this is another thing that I just kind of learned from a technician in one of my CO2 courses. He was like, because right now in the UK, if you can blow out the CO2, is that like you pump the circuit down, you say you have 12 bar left in a low temp circuit, or 200 psi, because that's vapor left. Right now you can still blow out all that CO2 to the atmosphere. It's not against the law anywhere in the world, I don't think, at this point, or there's not much regulation, but we can release natural refrigerants. But what a lot of people don't think about, and that I talk about in my training, and then it was a really good point a technician brought up in the course. He's like, I say you got to reclaim that, put that back in the system. Another technician, well, why would I do that? It's natural. It's not against the law. This technician told me, Trevor, at one of my sites where we have a lot of reliefs happening, it's having a lot of reliefs. Do you know that all the trees are dead around it now? All the grass is dead around it. And he says, Trevor, it's not. And he told the group, he told all the other technicians, he said, Trevor, it's not the releasing of the CO2. It's the oil that may be in that CO2 that you're releasing out. And so this is why in my trainings, I'm like, get a recovery unit, put it in. And I know it doesn't have, because when I started out in the field, it was a different time. But when he told me that, is like all the trees and all the grass is dead around where that relief is. So you guys got to think about that. It's not the CO2 is not a problem, but if you got POE flying out with it, because we know we have in that refrigerant going throughout the system, there's POE in there, all that refrigerant. So just think about that next time that you're relieving CO2 out of a system. A little tangent there. What are your thoughts on that? What are your guys' thoughts on that as well?
Yeah, absolutely.
Yeah.
You know, it's you've got to be mindful of the environment you're working in as well. You know, yeah. If you're having uncontrolled vents, you don't know what gas you're losing, you don't know what oil you're losing. It shouldn't happen anyway. It's a problem. Fix it. You know, be mindful of the environment.
It's something I didn't really think about.
Sorry,
go ahead,
Chris. To task on this. That's right. Try taking multiple companies to task on this of when are they going to release a suitable method for recovering CO2. And there are no plans out there. It's because we're starting to get to systems which are approaching their end of lives. 15 years, it'll be 15, 17 years, some of them, they're at the end of life. But currently, it is, as you said, it is release it to atmosphere rather than try and use it again. I know, again, global warming potential is way down there, but surely we should be looking at any refrigerant release is unacceptable and it should be reused because the process has gone into producing that CO2 and using it. Why let it go to waste? Why let it into the atmosphere? Let's just reuse it. And unfortunately, we haven't got a lot of cases where your new system is run up or in a position to run up before your old one is decommissioned. And you could just pull the CO2 over. Unfortunately, in an ideal world, that'd be great, but we don't. But there is nothing out there, and every company I've spoke to on this matter just has no interest in actually looking into it and producing something for it. So until regulations and laws change, I don't think there's going to be a real drive towards it.
Yeah, I know we're a little bit off topic here, but and don't get me wrong, everyone listen, I've let a lot of CO2 out. I used to do trainers and it was 50 pounds every training that I was letting out. So it's not like I haven't done it. But the thing is, we got to be cognizant of what we're doing. And when he talked about that, the POE going on, it just kind of clicked for me a little bit more. So, and reclaim, you can use reclaimers. The reclaimers that you're using now today, you can use that on CO2 as long as the pressure is low enough. Think about 410. If you use a reclaimer for 410, low temp CO2 or subcritical CO2 is the same pressure. So just look into that for the manufacturer of that equipment, because I know lots of technicians using reclaimers for CO2 vapor and stuff like that. That's below the pressure threshold. Okay, so let's get on with some more troubleshooting, Chris.
Oh, so John, I'll let you tackle this one on checking ETV stator coils.
Yeah, so it's just to know if you're sort of in a quandary between whether it's the valve that's failed or the stator coil that drives the valve. You can actually measure the resistance between the pins to check that. So you should be seeing sort of 35 ohms between 1 and 3 pins and 2 and 4 pins. So it just sort of helps you diagnose that fault.
And so what could cause a stator coil issue? And what have you seen in the past, John?
They can sort of short out over time. Obviously, they're sort of sat on the valve, so they're getting cold. They're in a moist environment. You know, they can fail and stop driving.
Yeah, I've definitely seen, well, not this specific one, but I've definitely seen them unhooking them from the valve and they're all rusted inside just because the moisture. And one thing too, like if you work in a supermarket, there's meat rooms and stuff, and so they're just spraying down everything, all the walls, and water splashing up on the coil, and they could fill up either the transducers or the electronic valve cable. So one contractor about 8 or 9 years ago, he's like, Trevor, we use heat shrink. So all their electronic valves in the wet, moist areas, they'll pull a big piece of heat shrink over it, so it will, any water that gets onto there doesn't really get into the valve itself. So it reduces some rusting and things like that, water getting into the valve.
Yeah, stop the ingress. Yeah.
Good idea. All right, on to the next one. So right-hand picture here is from a flash gas bypass valve, wasn't it, John? Again, very blocked up. Was it PRV or was it the high pressure valve? Sorry.
I think that was a high pressure valve, that one.
It's stainless steel, this one.
Wow.
Yeah. Do you want to talk about the... Sorry, guys.
Yeah, that there can cause a massive amount of issues. Now, your high pressure valve is really the control of your system. it's controlling your gas cooler condenser, it's controlling your receiver. And then you start plugging that up, it could cause issues in a lot of different places. And, you could be out at a case, that last case is not feeding. You could be looking at the flash tank, the flash tank, hopefully you understand that the high pressure valve goes into the flash tank receiver, but it could cause some issues other places in the system, and you're looking there, but it comes back to the flash gas. What are some troubleshooting tips, John, that you've used over the years when you're running into, like, say, a high pressure valve issue like this?
Obviously, check your trends. Look for sort of spikes in pressure, increases in pressure. Check your ambient temperatures as well and how that sort of correlates to the pressures you're seeing. General sort of instability in the system as well. As you say, your receiver fluctuating. It's not good. You start hitting sort of high pressure shutdowns. Yeah, it's not good.
Yeah. Totally. And so this is important to understand. Like, if this starts to plug up, it's going to mess up your whole system. You need your high pressure valve, your flash gas bypass valve, and all your EEVs to work in sync. And so when you have those working in sync, you're going to have a system running really, really good, stable suction, stable liquid, and really a stable discharge. And this comes back to fine tuning, which is a whole nother conversation with electronic valves and controls. Yeah.
And that sort of text to the side of that just sort of shows the ability you've got with I think it's the Corel EVD Evo, where you have an interchangeable display. You can actually upload the settings to the display, have that as a backup. So if that valve driver ever fails, you can actually take the display off, put it back on, download the settings, so it saves you a lot of time. Equally, if you've got another pack on site, you've got a second display, you can upload it, transfer it across. As long as it's the same, obviously, system and it's commissioned the same, then it can save you a lot of time and headache. So,
love that.
Some of the end users who invest in like a remote monitoring system, they can have it so every 24 hours it just broadcasts what the site conditions should be. So even if you change a component, you can input your parameters. If they're slightly wrong, it will get that updated broadcast to take it back to what the conditions should be, ideally. That's one way, which is a good time saver as well. If you had multiple fixtures that you've replaced, you just leave it in their capable hands, assuming that it is actually set up correctly. Just saves that time-consuming process of going through and inputting 40 different parameters on every single cabinet controller. I know it's slightly off topic then in terms of Superheat, but so like Superheat and valves go quite closely hand in hand. And again, there's a lot of valves on the CO2 system, so let's discuss them.
Yeah.
So perfect. With that in mind, Trevor, that was everything we wanted to show today. So again, any questions?
Yeah, so there was one question by Andrew Freeber, a good friend of mine, been in tons of training, ambassador of the refrigeration mentor community. And this would go back to the oil, I think, in the transducer. What would you recommend if you do get oil or have oil in the transducer? And he kind of answers, I feel like something needs to change because if it happens, one of the most likely happens again. It's like anything. It's you don't want to put a TX bulb at the bottom of a pipe because oil is going to insulate it there. I've seen manufacturers where they would put a quarter-inch pipe a certain distance away so oil doesn't get into the transducer, for an example. That's just one example. That might be extreme. But you never want to put a transducer in the bottom of a pipe because that's where the oil is coming back up the suction and could fill it right up. So I would definitely take a look at the piping and adjust if needed. What are your guys' thoughts?
Exactly what I'd recommend there is, where possible, particularly on cold rooms or walk-in freezers, if you can access above the room at the top of the suction riser, is put the transducer there, because ideally any oil which has made its way up there will then continue to flow back to the compressor. It's not like if we sat it at the bottom before it rises up that riser, but any oil can pull back down and potentially flood it. That's not always possible on sales floor fixtures. If you have very high ceilings or inaccessible ceilings, you obviously wouldn't put it up there because it does need to be maintained and accessed. At which point, then, as you said, Trevor, actually put it on a stub with a bit of physical height to protect it from oil logging. That'd be my solution.
Yeah, or a fallback to the suction pipe, so that the oil flows back into the suction.
Yeah, exactly. That's the best case scenario. Another question here. So, good friend Jason, hey Jason, shout out to you being at all these CO2 experts over the last a few months. I know that Appian reclaimers have an internal high pressure check cutout because of the PT relationship of CO2. I'm not sure the reclaimer would stay online unless the vapor pressure was greatly reduced. If the case or rack is pumped down, the service pressure will equalize to ambient condition using 60 Fahrenheit example. The thing is, though, Jason, I'm talking about vapor. So CO2 vapor, it's not going to increase like liquid. So if you pump down, my example, you pump down a circuit, you pump all the liquid out of the circuit, and you only have CO2 vapor inside that, you could use the reclaimer to pull out that CO2. So if it's 200 psi, it's not like it's going to raise up to 1,000 psi in that reclaimer, if that makes sense. Any thoughts on that, John or Chris? Did you guys use reclaimers lots in the past?
Well, CO2, I'm just thinking, even with good sort of vapor density of CO2, I just think it'd take a long time to reclaim anything, particularly on a large system. But I suppose if we're going to be doing that, you'd be there for the whole day. It's got to be something to overcome it. I wouldn't personally want to use a system or a recovery rig which wasn't rated or tested on CO2 yet. But that's what I'm thinking. The manufacturers need to come up with this. The tool manufacturers, they need to come up with a solution for it. We'll leave it in their capable hands. All I'll do in the meantime is complain.
Yeah. And Stephen, that's a good point. Stephen says you still got to condense into the cylinder. I'm just talking about pumping it right back into the system, if you can, like somewhere's in the system, which might or might not be possible. And standard cylinders are going to very quickly increase the pressure. Yeah. I don't even think there's recovery cylinders for CO2 that I know of yet. I've heard of people making them, but I'm just talking about just pumping it back into the system, so you're not really using any. And once again, we're just trying to come up with ideas here and to make it easier for us. And that doesn't make it easier for us, but we don't want to be throwing POE all over the place either. Guys, I love this. Like, I learned a ton. John, it was so great to meet you. Chris, as always, I appreciate you taking the time. And I'm excited about all the things coming up. This is 2025. We're just getting kicked off here. This is going to be a good year for refrigeration. It's going to be a great year for CO2, natural refrigerant, but it's going to be great for all the people who are enrolled in our CO2 advanced design course too, Chris. I'm super pumped up for this because over the last year since we started training design, my background is technician. I was in the field doing install, just like John, doing service, doing support, work for a manufacturer. But ever since I started working with you and Omega Solution and we started doing these design courses, I'm definitely a better technician, because now I can understand the engineering behind why something works. And before we end off here, what are your thoughts on that, John? Because I know your background started as a technician. Over the years, you have to learn design to support your team and all the people there. What are your thoughts for technicians starting to learn design throughout their career, and how can that benefit them?
Well, if you can underpin the practicality on site with the technical aspect and you understand it, obviously you'll be able to diagnose the fault significantly quicker and a lot more accurately as well. So it's key, really. You need to understand what you're looking at.
Yeah. Chris, any final thoughts, brother?
The main thing was it gave you almost additional options that you would never have considered when you would just, I'd only repaired and replaced equipment rather than having to actually think about how it's designed from first principles. For example, as we touched on the pipework last time, it's no longer a case of it possibly being a component issue. It's a network infrastructure issue, but without having that sort of theoretical knowledge and understanding how fluid flows within a system and what pitfalls can occur, you would never know what to deal with in that sense. you might have a gut feeling about that pipe looks a bit smaller than I've normally seen connected to this many cabinets. But until you actually understand and possibly have to verify it through software, but it gives you that option to think, actually, that's the correct solution, we'll go down that route. It's not the cheapest solution always, but if it guarantees, ideally fault-free operation for the next 10 years, how many callbacks have you saved yourself going to site trying to drain oil out of an evaporator to get the system back up and running? You probably save that amount of money just in oil that you're having to reuse each time. It gives you that full picture of a system. Now, I find design can be, often there's almost three pillars: as service, as installation, and as design. And having all three pillars there, it rounds out the picture. I think it makes you the full engineer that you can be.
No, and I totally agree. Like 100% better at troubleshooting system, because understanding the design of something, not only understanding the design, but how to design it. And then it gives you it gave me or helped me think differently when I look at a designer. So there's so many big, awesome, great manufacturers that I work with and we work with around the world. And when you look at each other's design, that there's lots of differences, unique differences, but it's still refrigeration. It's the same. And so if a problem does arise and you understand what their thought sequence was and why they were trying to do something, because they're always trying to make it better. It's not like these manufacturers are building equipment to make them worse. They're trying to make it better. But when you understand the design side, you can actually go in and plug stuff in very quickly. Where, at first I thought, okay, how do I size these 4 compressors for this capacity? And then all of a sudden I plot it out and I'm like, okay, this makes sense now. This is my total heat of rejection. Why I have this. This is my discharge, what it should be. And then, you plot that inside the different softwares like the Bitzer or the Bach or the Danfoss or the Copen, whatever it is. And then you can see either the issues or how it works. Anyway, for me, design has definitely changed the game for CO2. That's for sure. Awesome. Well, once again, I want to thank everyone for taking the time to come and listen. So once again, if you're listening on the podcast, hit the like, hit the share, comment what you think about this podcast. Or if you're on the YouTube channel, same thing, like, share, comment. This is how more people find out about it. So we really can help the industry grow and get better and learn more. Chris, John, thank you so much for being on CO2 Experts, and look forward to chatting with you guys again soon. See you, everyone.
My pleasure.